Good morning, friends. Today we are discuss about the heat treatment processes. My name is Dr. N.S.T. Rangarajulu, Assistant Professor, Department of Production Technology, MIT Campus, Anna University, Chennai. So what is mean by heat treatment? Heat treatment is nothing but you can heat the material to the required temperature. Then you can hold for some time. After that, you can able to make a cooling, slow cooling or fast cooling. Based on that, you will get the required hardness. So this is one of the worker makes a hardening heat treatment of the metal gear on a special machine, close up, hardening of metal and conching. And another one is a heat treatment of iron for forge for further use. And then knives also they can able to make a heat treatment. These are all the things we'll discuss. So first a brief introduction about these things. Brief introduction about the heat treatment processes. So first one is a heat treatment. Heat treatment is nothing but you can heat the material to the required temperature, then hold for some time. After that, you can able to make a cooling to the fast cooling or slow cooling. Based on that, you will get the hardness. So that is the heat treatment process. Generally, we are discuss about this before heat treatment process. You know about the iron carbon diagram and the triple T diagram, time temperature transition diagram. These things you know very well, then you can able to easily understand this concept of heat treatment process. Nothing but triple T diagram says that upper critical temperature is 912 degrees centigrade, lower critical temperature is 723 degrees centigrade. Then if you are making a upper critical temperature or above heat treatment process, then you can able to make a cooling suddenly. You will get the fine grains, that is a martensite structure. So that will give the high hardness of the material. Suppose you can able to make the cooling very slowly, you can get the coarse grained structure, that is a perlite structure. You will get the soften the material. So this is a heat treatment, brief introduction about heat treatment, and you can know about these things, then easily you can able to understand all the heat treatment processes. Now we are discuss about start about the video lecture for heat treatment process. Heat treatment is defined as an operation involving the heating and the cooling of the metal or an alloy in the solid state to obtain certain desirable properties without change composition. The process of heat treatment is carried out to change the grain size, to modify the structure of the material, and to relieve the stresses set up the material after hot or cold working. The heat treatment is done to improve the machinability, to improve the magnetic and electrical properties, to increase the resistance to wear, heat, and corrosion, and much more reasons. So heat treatment consists of heating the metal near or above its critical temperature held for a particular time, at that finally cooling the metal in some medium, which may be air, water, brine, or molten salts. The heat treatment process includes annealing, case hardening, tempering, normalizing, and conching, nitriding, cyaniding, etc. So types of heat treatment processes. Following are the different types of heat treatment process. Annealing. Annealing itself, so many annealing processes are there. Normalizing, hardening. Hardening also different types of hardening is there. Tempering, nitriding, cyaniding, induction hardening, flame hardening, etc. So we are discuss about first annealing. Annealing is nothing but you can able to soften the material. Annealing is one of the most important process for heat treatment. It is one of the most widely used operations in the heat treatment of iron and steel, and it's defined as softening process. Heating from 30 to 50 degrees centigrade above the upper critical temperature and cooling it at a very slow rate by seeking it the furnace itself. The main aim of the annealing is to make steel more ductile and malleable and to remove internal stresses. This process makes the steel soft so that it can be easily machined. Purpose of annealing is to soften steel and to improve the machinability, to refine grain size and removes gases. It removes the internal stresses developed during the previous processes to obtain desired ductility, malleability, and toughness, to modifies the electrical and magnetical properties. So procedure for annealing, depending on the carbon content, the steel is heated to a temperature of about 50 degrees centigrade to 55 degrees centigrade above its critical temperature range. It is held at this temperature for a definite period of time, depending on the type of furnace and nature of work. The steel is then allowed to cool inside the furnace constantly. So application of annealing, it is applied to casting and forging components. Common applications for annealed metals include work hardened materials such as sheet metal that has undergone a stamping process or cold drawn bar stock, metal wire that has been drawn from one size to smaller size may also undergo an annealing process. Machining operations that create high amounts of heat or material displacement may also warrant an annealing process afterwards. Welded components can create residual stresses in the area of the material exposed to elevated temperatures. To recreate uniform physical properties, annealing is often used. So advantages of annealing. The advantages of annealing are as follows. Annealing makes the metal softer. The lessens thermal stresses brought on by temperature differences. It increases and strengthens the steel's machinability. The metal becomes more ductile as a result. Annealing increases the metal's tensile strength. It enhances the metal's uniformity. In the steel has finer particle size. Annealing gets the steel ready for additional thermal treatment. It results in a particular substructure. Some disadvantages, some major disadvantages are as follows. The major drawback of annealing is that it needs exact temperature controlled throughout the heating and cooling cycles to keep uniformity throughout the part being treated. This means that it needs to be done cautiously to prevent thermal shock, which is then incorrectly could lead to fracturing. Additionally, some materials might need multiple cycles to produce the best results, which increases the time and the expense involved in the carrying out this operation. Annealing may not be effective on all materials. Annealing can cause defects. Annealing may alter the properties of the material. These are all some of the disadvantages of annealing process. Next treatment is normalizing. Normalizing, the main aim of normalizing is to remove the internal stresses developed after the cold working process. In the steel is heated 30 to 50 degrees centigrade above upper critical temperature and cooling it in the air. It improves the mechanical and electrical properties, machinability, and tensile strength. Normalizing is the process of heat treatment carried out to restore the structure of normal condition. Purpose of normalizing, promote uniformity of structure to secure grain refinement, to bring about desirable changes in the properties of steel. Procedure for normalizing, the steel is heated to a temperature of about 40 to 50 degrees centigrade above its upper critical temperature. It is held at this temperature for a short duration. The steel is then allowed to cool in still air at room temperature, which is known as air quenching or normalizing. Applications of normalizing, It is applied castings and forging to refine grain structure and to relieve stresses. It is applied after cold working, such as rolling, stamping, and hammering. Some other applications of normalizing are it is used in some plate mills in the production of large forging, such as railroad wheels and axials, and some bar products. It is utilized for both brackets and sheet metal forging. Casting internal stress is relieved with it. It is employed to restore the internal mechanical characteristics of cold worked or forged steel. In order to lessen the hardness that develops during the forming processes, it is utilized for ferritic stainless steel stampings in the automotive industry. So, difference between annealing and normalizing. Annealing, after annealing, the most metals are cooled in the controlled cooling inside the furnace. Normalizing, after the normalizing, the metals are cooled in ambient air outside the furnace. The cooling rate after annealing is comparatively slower. The cooling rate after normalizing is comparatively faster. Results in relatively higher ductility in annealing, results in relatively lower ductility in normalizing. Annealing results in relatively lesser hardness, strength, and toughness. Normalizing results in relatively higher hardness, strength, and toughness. Annealing results in a coarse and less uniform grain structure. Normalizing results in fine and more uniform grain structure. Internal stresses after annealing are minimal. Internal stresses after normalizing are slightly higher. The cost of annealing is high. The cost of normalizing is low. Metals and metals alloys like steel, aluminum, brass, and copper undergo annealing. Mainly stainless steel, aluminum, brass, and copper undergo normalizing. Applications, mechanical components, electrical components, and household items. Applications in normalizing, automotive industry, nuclear industry, and construction industry, etc. So, advantages of normalizing process. Some of the advantages of normalizing are it increases the microstructure's homogeneity and refines the grain size. It decreases the possibility of distortion or fracture by releasing internal stresses. To improve the metal's ductility and hardness, the metal becomes stronger and harder as a result. It eliminates any remaining dendritic segregation from the casting processes. Some disadvantages of normalizing processes are it may overcomplicate the metal structure by breaking it into too many tables. It may reduce the strength of some alloys and metals. It may require subsequent machining or surface finishing to remove the scale or decarburized layers. Next process is hardening process. Hardening, the main aim of the hardening process is to make the steel hard, tough. In this process, steel is heated 30 degree to 40 degree centigrade above the upper critical temperature and then followed by continuous cooling to room temperature by quenching in water or oil. It is the opposite process of annealing process. The purpose of hardening, by hardening, it increases the hardness of steel to resist to wear, allows the steel to cut other metals. The procedure for hardening, the steel is heated above its critical temperature range. It held at a temperature for definite period of time. The steel is then rapidly cooled in a medium of quenching. The quenching medium is selected according to the degree of hardness desired. The air, water, brine, oil, and molten salts are used as quenching mediums. A thin section, such knife blades, are cooled in air. Water is widely used for medium, but it results in the formation of bubbles on the surfaces of the metal. So, procedure for hardening continues. Hence, brine solution is used to prevent this. Oil is used when there is a risk of distortion on cracks and is suitable for alloy steels. The molten salts are used to cool thin section to obtain crack-free and impact resistant products. Application of hardening. It is applied for chisels, sledgehammer, hand hammer, center punches, tabs, dies, milling cutters, knife blades, and gears, etc. Some other applications in case hardening are forging presses, fasteners, metal rolling equipments, camshafts, machine tools, rods, drive lines of mining equipment and heavy duty transmissions, cutting tools, automobile spares, aerospace components, etc. So advantages of case hardening. Some of the advantages of case hardening are the boosting steel parts, wear resistance and fatigue life. It increases their longevity and economical use. By forming a hard top layer over a soft core, it enables the use of steel with greater machinability for heavy duty applications. By lowering the possibility of distortion or fracture, it makes the steel more weldable. By creating a protective coating on the surface, it improves steel's resistance to corrosion. Steel's appearance is enhanced by giving the surface a more appealing gloss. Some disadvantages of case hardening are it can be costly procedure that calls the specialized tools and expertise. It may cause hardness variations which could reduce the metal's overall strength. Metal may get distorted as a result, which could make working with it more challenging. It may increase the possibility of chipping or cracking, which could shorten the metal's lifespan. If done incorrectly, it may increase the metal susceptibility to corrosion. These are all the some of the disadvantages of case hardening. And the next operation is tempering. Tempering, when the hardening process hardens a steel specimen, it becomes brittle and has a high residual stresses. It is an operation used to modify the properties of steel hardened by quenching for the purpose of increasing its usefulness. Tempering or draw results in a reduction of brittleness and removal of internal strains caused during the hardening. After the hardening, we will make a tempering. Then you can reduce the internal stresses, remove the internal stresses, and caused the during of hardening. Steel must be tempered after the hardening process. Tempering. The tempering is divided into three categories according to the usefulness of steel required: low temperature tempering, medium temperature tempering, high temperature tempering. So purpose of tempering: to relieve internally stress caused by the hardening, to reduce brittleness, to improve ductility, strength and toughness, to increase wear resistance, to obtain desired mechanical properties. Purpose of for tempering: the steel, after being quenched in the hardening process, is reheated to a temperature slightly above the temperature range at which it is to be used, but below the lower critical temperature. The temperature here varies from 100 degrees centigrade to 700 degrees centigrade. The reheating is done in a bath of oil or molten lead or molten salt. The specimen is heated in the bath for a period of time till attain the temperature evenly. The time depends on the composition and desired quality of steel. Now the specimen is removed from the bath and allowed to cool slowly in steel air. The application of tempering: it is applied to cutting tools and gears which are hardened by the hardening process. So the benefits of tempering: increased ductility and flexibility, reduced brittleness, excess of hardness can be adjusted to acceptable levels, improved microstructure which increase the metal strength, relieves internal stresses occurred from period of prior operations. It left unchecked residual stresses may cause hydrogen cracking, increased wear resistance properties of the surface as well as the core. The tempered steel is durable and long lasting, increased machinability and formability for succeeding processes, increased toughness. Tempering is quicker than the annealing process. Tempered steel is also harder and stronger than the annealed steel. So next process is nitriding. Nitriding is the process of case or surface hardening in which nitrogen gas is employed to obtain hard skin of the metals. In this process, steel is heated in the presence of ammonia environment. Due to this, a nitrogen atom is deposited and makes material hard. Induction hardening and flame hardening objects are heated by an oxyacetylene flame. So purpose of nitriding, the harden the surface of the steel to a certain depth, increase the resistance to wear and fatigue, to increase the corrosion resistance. Procedure for nitriding, it is done in the electric furnace where temperature varying between 450 and 510 degrees centigrade maintained. The part is well machined and finished and placed in a airtight container provided with outlet and inlet tubes through which ammonia gas is circulated. In the container with the part is placed in the furnace and ammonia gas is passed through it while the furnace is heated. During the process of heating, nitrogen gas is released from the ammonia in the form of atomic nitrogen, which reacts with the surface of the parts and forms iron nitrate. In depth of entrance depends upon the length of time spent at the nitriding temperature. The part is taken out and it does not require any quenching or further heat treatment processes. So application of nitriding, it is applied for hardening the surface of medium carbon alloy steels. Best to use applications, the United States being developed nitriding process in the early 1900, but there was a little interest for industrial uses until after World War II. The application required to improve fatigue strength and precision, such as in extrusion screws and precision gears, gas nitriding is most appropriate. Highly stressed machine components and low alloy steels also benefit from the durability attained with this process. Low carbon steels tools may corrode sooner than expected without this case application. Automotive parts such as crankshafts, valve parts, and springs can maintain a level of malleability that prevents cracking under extreme conditions. Due to its enhanced corrosion resistance and anti-galling properties, it is a primary process used in aircraft components from pistons, rods, and spaces to shaft pins, nuts, and bolts. The advantages of gas nitriding, low cost compared with other case applications. The process runs with minimum required supervision. Post-process components are dimensionally stable and there is a very little, if any, treatment necessary is post-heat treat operations. Zero to minimal distortion experienced on parts, which enables prices, dimensional control, high volume capability. Furnace size is the primary limiting factor. Wear and corrosion resistant, increased fatigue strength, gas flow rate can be precisely controlled, and parts can be masked, preventing hardening in some areas. This allows for post-application machining. Clean parts are produced with none of the residues that accompany salt baths, carburizing, and other processes. Cyaniding. Cyaniding is the process steel is heated in the presence of sodium cyanide environment. Due to this, carbon and nitrogen atoms are deposited on the surface of the steel and make it hard. Purpose of cyaniding. This method is effective for increasing the fatigue limit of medium and small sized parts such as gear, shaft, wrist pins, etc. To increase surface hardness, increase wear resistance, to give the clean, bright, and pleasing appearance to the hardened surface. The produced for cyaniding, the parts to be treated is dipped in a molten cyanide salt bath maintained at a temperature of 950 degrees centigrade. The molten salts used are sodium chloride, sodium carbonate, sodium cyanide, and soda ash. to immersed article is left in the molten cyanide salt at a temperature of 950 degrees centigrade for about 15 to 20 minutes. The decomposition of sodium cyanide yield nitrogen and carbon from the carbon monoxide, which is diffused into the surface, resulting in hardening the surface. The parts is then taken out of the bath and quenched in water or oil. The application of cyanide, it is applied to small article like gears, bushings, screws, pins, and small hard tools which require a thin and hard wear resisting surfaces. Applications of cyanide. Cyaniding is a popular surface hardening process used in many industries to improve the wear resistance and durability of low carbon steels. Some applications of cyaniding. Automotive industry, cyaniding is used to harden the surface of the gears, camshafts, and other components used in vehicles. This process helps improve the wear resistance and fatigue strength of these parts, which is essential for reliable performance. Aerospace industry. In the aerospace industry, cyaniding is used to harden the surface of the components such as landing gears, and other critical parts. In this help ensure that these components can be withstand the harsh operating conditions and high stresses they encounter during flights. Tool and die industry. The tool and die industry uses cyaniding to harden the surface of cutting tools, dies, and other components. It helps improve the wear resistance and extend the life of those tools, which is essential for efficient production. Firearms industries. Cyaniding is commonly used in the manufacturing firearms, where it is used to harden the surface of parts such as barrels, bolts, and triggers. This helps to ensure that these parts can withstand the high stresses and repeated firing associated with firearms. Oil and gas industry. Cyaniding is used in the oil and gas industry to harden the surface of the components used in drilling and production equipments. This helps to improve the wear resistance and extend the life of these components, which is essential for efficient and safe operation. Overall, cyaniding is a versatile and widely used process that can be provide benefits in the terms of wear resistance and performance across many different industries. Advantages of cyaniding. Increased hardness. Cyaniding increases the hardness of the metal surfaces by up to 30%, which makes it more resistant to wear and tear. Improved wear resistance. The surface layer of the metal becomes more resistant to wear and abrasion, which increases the lifespan of the part. Reduces friction. The low coefficient of friction of the surface layer reduces the friction between moving parts, which improves the efficiency and reduces wears. Improved fatigue strength. Cyaniding can improve the fatigue strength of the metal by creating comprehensive stresses on the surface layers, which reduces the likelihood of cracks forming and propagating. Cost effective compared to other surface hardening processes such as carburizing and nitriding. Cyaniding is a relatively low cost process. Versatile. Cyaniding can be used on wide range of metals, including low carbon steel, medium carbon steel, and alloy steels. This is used for cyaniding is used for low carbon steel, medium carbon steel, and alloy steels also. Next one is carburizing. Carburizing. In this process, steel is heated to the presence of carbon environment. Due to this, carbon atoms are deposited on the metal surface and make it hot. Applications of carburizing. It is used extensively in the automotive and aerospace industries, where wear and corrosion resistance are critical factors. Parts that are carburized often last longer and perform better than the non-carburized parts. Advantages of carburizing. Carburizing parts have advantages over a non-carburized parts such as increased wear resistance and corrosion resistance. Increased wear resistance. Carburized parts are more wear resistant than non-carburized parts because the carbon content forms a hard wear resistant surface layer. Increased corrosion resistance. The carbon content also forms a protective layer that resists corrosion. Increased hardness. Carburizing increases the hardness of steel, making it less likely to deform or fracture. The advantages of carburizing: improved machinability. The increased hardness of carburized steel also makes it easier to machine. This is mainly used to prevent the breakdown of high stress, high capacity machineries such as gears, ball bearings, and other internal rotating parts. It does this by causing the conversion of some steel into carburized iron, which is tougher than the steel but less tough than cast iron. It produces parts that can withstand tremendous punishment and keep them looking shiny and new, like they are new again, no matter how rough you use them. Just don't expect it to keep the rust away. Carburizing also hardens the metal parts, which can help them to maintain strength under heavy use. Disadvantages of carburizing: it reduces the ductility of the steel and requires long heating and cooling times. Reduced ductility. Carburizing makes steel less ductile because it reduces the amount of free ferrite, which is capable of deforming without fracturing. Long heating and cooling times. Carburizing requires long heating and cooling times at high temperatures between 1300 degree Fahrenheit and 1600 degree Fahrenheit. This makes the process very time consuming. Increased machining cost. The increased hardness of the carburized steel also makes it more difficult to machine, resulting in increased machining cost. Increased weight. Carburizing increases the weight of the steel parts because of the added carbon content. Carburizing is very popular heat treatment process. A disadvantages of carburizing is that while increasing mechanical strength, it decreases ductility and toughness of low alloy steels. That means that they are more prone to cracking during physical impact or welded joints, especially when the end workpieces are extruded profiles with round wires ends or long cylindrical products where bending strains are concentrated during welding. It reduces aesthetics such as coloration and polishing because after carburizing, you must polish to reveal the surface. Last one, case hardening or surface hardening. The main aim of this process is to make the only external surface of steel hard and inner core soft. It is the process of carburization, that is the saturating of surface layers of steel with carbon or some other processes by which case is hardened and the core remains soft. Case only hardening, core remains soft. This is the impact and impact load. Wherever the impact load will act for connecting rod, camshaft, crankshaft, and other parts, we can able to make a case hardening alone required. Inner is soft core is required. So that time we can use for case hardening purpose. Purpose of case hardening: to obtain a hard and wear resistant to machine parts. By case hardening, it obtain a tough core to obtain a higher fatigue limit and high mechanical properties in the core. The surface hardening and case hardening. The difference between the surface hardening and case hardening: surface hardening is the process of increasing the hardness of the outer surface while the core remains soft. Case hardening is the process of hardening the surface of a metal by infusing elements into the metal surface, forming a thin layer of a harder alloys. There are several ways to harden surfaces, including induction hardening, flame hardening, laser hardening, etc. There are different methods of case hardening such as carburizing, nitriding, cyaniding, carbonitriding, etc. Depending on the type of composition of the metal and the desired properties of the finished product. Then surface hardening done by heating the steel up to actiniting temperature while keeping the core below that temperature and quenching for surface immediately. Case hardening done by red heating the steel, infusing carbon into the surface and quickly quenching. Surface hardening used for many equipments made from steel. Case hardening commonly used for low carbon metals alloys such as mild steel. Case hardening only you can use for low carbon steels, mild steel and other things. Then only you can able to toughen the surface of the layer. Required immediate quenching for surface hardening, does not require immediate quenching for case hardening process. These are all the some of the difference between surface hardening and case hardening processes. Purpose of heat treatment of steel. The following are the purpose of heat treatment: to improve mechanical properties such as tensile strength, hardness, ductility, shock resistance, and resistant to corrosion. Improve machinability, to relieve the internal stresses of the metal induced during cold or hot working processes. To change or refine grain size. Improve the magnetic and electrical properties. Increase the resistance to wear and corrosion. To increase the surface hardness. So thank you for your listening. Today we have discussed about different types of hardening processes: annealing, normalizing, tempering, hardening, and carburizing, case carburizing, and surface hardening processes, and all those things. This may be very useful for your metallurgical aspect, any heat treatment processes. This is very simple concept. I will tell you the application of the heat treatment process, advantages, limitations, and applications, and all those things. Without carbon content, you may not able to make a harden the steel material. Based on the carbon content only, you can able to make a heat treatment process. And heat treatment process also, if you are above the upper critical temperature, below the lower critical temperature, you know about the upper critical temperature is 912 degrees centigrade. Lower critical temperature is 723 degrees centigrade. And based on that, due to the carbon content, time temperature transition diagram, based on that, Martensite start and Martensite to finish. Based on that, we can able to detailed manner we will discuss. You know very well about the time temperature transition diagram. Then easily you can able to understand these heat treatment processes. Time temperature transition diagram and iron carbide diagram is very important in a metallurgist. So based on that, we will be able to discuss about some of the heat treatment processes and advantages, limitations, and applications, and all those things. Thank you very much for your patient listening. Thank you. It may be very useful for you. You can able to like the videos and you can circulate among your friends, groups. Then it may reach the higher level. Thank you very much for your kind attention. Thank you. Thank you.